Yeah. So, am I audible? Okay. So, good afternoon, everyone. So, welcome to our next session. That's the session 8, and which will be mainly on the FPGA-based biomedical signal processing with AI/ML approach. So, let me introduce the speaker of this session, Dr. Rajesh Tripathy, a senior IEEE member with PhD BTech degree and Medical Engineering from Biju Patnaik University of Technology, Lamsala, the MTech degree in the Biomedical Engineering from the National Institute of Technology, Lamsala, and the PhD degree in Electronics and Engineering from the Indian Institute of Technology, Guwahati, India. As an assistant professor with the Faculty of Engineering and Technology, FPT, which was Anusandhan from March 2017 to June 2018. Since July 2018, he has been an assistant professor with the Department of Electrical and Electronics Engineering, Birla Institute of Technology and Science, BITS Pilani, Hyderabad campus. He has published research papers in reputed international journals and conferences. His current research interests include machine learning, deep learning, architecture design, vector data processing, medical image processing, embedded artificial intelligence, and the Internet of Things, IoT, for healthcare. He has served as a reviewer for more than 15 scientific journals and a technical program committee member for various national and international conferences. He is an associate editor of IEEE Access and Frontier in Physiology. Welcome to you, sir.
Yes. So, yes, thank you, Professor Raj, for the introduction. So, am I audible? Am I audible?
Yeah, you are audible, sir.
Yeah. So, the slides are visible or not?
Slides are visible. If possible, you can make it in the slides more, sir.
Okay. Okay. So, so thank you for the opportunity. For this opportunity, actually. So, I'll give the talk regarding the recently published work on embedded artificial intelligence for detection of breast cancer using ultrasound images. So, so the objective of this work is mainly to develop one lightweight deep learning architecture and its implementation on PinkJet2 FPGA for real-time detection of malignant tumor, or we can say that is the breast cancer using ultrasound image. So the first thing is why the breast cancer detection is extremely important nowadays. So as we know that this breast cancer continues to be the primary cause of high mortality rate in India as well as globally. So that is why the early detection of this disease is very challenging in clinical standard for the accurate diagnosis and obviously the diagnosis as well as prognosis also. So that is like for diagnosis of breast cancer, normally the mammography is used. So mammography is a low dose X-ray based imaging so for the diagnosis of breast cancer. So also this type of imaging has the drawbacks that if you do the mammography repeatedly, so when the non-ionizing radiation so falls in the breast tissue, obviously that can proliferate the breast cancer. So that is why this is the main drawbacks of mammography, and also it has the limited sensitivity for the dense breast tissue in younger women. So that is why so mammography is not recommended normally for the as the imaging modality for the diagnosis of breast cancer. So what other modalities we have? So we have other modalities are like magnetic resonance imaging and positron emission tomography. So these two imaging techniques are very costly imaging techniques, and they require obviously trained and experienced professionals for the diagnosis of breast cancer. So what alternative we have? So we have the alternative as ultrasound. So as we know, ultrasound is a very non-invasive technique, so that mainly consider the sound waves to produce the image of the breast. That means the area where we can localize the cancer, whether it is benign or malignant, all those things. So that is why ultrasonography has the advantage that it helps to distinguish the fluid filled cysts, as well as it is very helpful for diagnosing the breast cancer in dense breast tissue. So that is why this ultrasound imaging is very challenging, and it is very popular for the diagnosis of breast cancer. So obviously, when the ultrasound images are generated, the radiologist normally see the morphological changes in the ultrasound image for the diagnosis of breast cancer. So that is again very cumbersome process. So that means it requires experienced and as well as the skillful radiologist for diagnosing the breast cancer. Now imagine, so we have one like suppose AIMS Delhi or any other AIMS institute. So we have so many patients are there. So and very limited radiologists are there in the India. So how can they diagnose all ultrasound images? So that is where artificial intelligence comes to picture. So where the automated algorithms are developed for the detection of breast cancer using ultrasound image. So that is the motivation why we go for the artificial intelligence based algorithm for early detection of breast cancer. So then the next part is, so when we develop the AI algorithm, so obviously we'll target, so that means where we need to deploy, because the final thing is to deploy the algorithm on cloud or on the edge device. So that is, there are many advantages for the cloud based deployment of AI algorithm, and also many shortcomings are there for the cloud based deployment. So the advantage is that it provides the user friendly framework, so where you can use at anywhere this framework for the diagnosis of breast cancer. Just you need to upload the ultrasound image, and now the AI model is already uploaded in the server, such that you can finally get the whether it is benign class or malignant class. So it's very user friendly. But the problem in the cloud based framework that it has high latency, and the privacy and security of the ultrasound image is not there when we consider the cloud based processing, because you are directly uploading the data ultrasound image in the cloud server. So obviously so there is a chance that privacy or the safety of your ultrasound data may alter. So that is why, to overcome all those things, as well as the latency is also high when we consider the cloud based implementation. So normally, so when we consider this cloud-based implementation and also any alternation in the model parameter, suppose you have already developed the AI model. So tomorrow you need to alter the model. So that means you need to change the weight and the bias parameter. So obviously, so any alternation, so that will again cause problem regarding the latency as well as the privacy and other things. So to overcome all those things, so that is a on-device implementation of a privacy preserving AI model is normally used in healthcare system for diagnosing the various diseases. So out of that, obviously the breast cancer is one disease where we can say the on-device implementation is extremely challenging. So that is a various edge computing devices are already there. So we have microcontrollers, we have Android, we have FPGAs, and also dedicated ICs like your ASIC, so all those things. So why FPGA is normally used? So FPGA is used because of the low power, low latency, then also the function acceleration. So we can accelerate the deep learning algorithm based on obviously various factors are there. I'll discuss all those things in the subsequent slides. So obviously when we consider about the FPGA, so there is one thing comes to your mind, that obviously it is parallel processing, low power, low latency, as well as the adaptability, and then also the function acceleration. So that is why FPGA devices are nowadays widely used for healthcare applications. So obviously when we considering about the breast cancer detection, so obviously the existing methods, what they consider, so they consider the very like huge deep learning model. So huge deep learning models means, so the model has obviously more than 25 million parameters, or we can say more than 1 lakh parameters. So what do you mean by parameter? So parameter means any AI model, obviously, so if we have the image, So then we need to evaluate the feature map. So obviously we need to multiply the weight matrix plus bias, then we need to consider the activation function. So when we have the weight matrix, so if we have the weight matrix, that means at the different layer, so we have different weight matrix values. So obviously when we consider the deeper network, so obviously the weight parameters increases. So in that case, to implement that network on edge device with limited resource is again very challenging. So whatever the existing methods are there, they have used various deeper models like your BusNet and MSA DIDL. So BusNet stands for Breast Ultrasound Image Network, and MSA DIDL stands for Multi-Scale Attention Domain Interpretable Deep Learning. So these two models have more than 1 lakh parameters. Similarly, other models like RetinaNet, Faster RCN, and YOLO V2, which normally uses the VGG, as well as the cascaded residual convolutional neural network. So these models has more than 1 lakh parameters. And also one more thing is, when the model parameter increases, obviously the latency again increases. So our objective is to reduce latency. So how can we reduce latency? So obviously we need to reduce the model parameter. So that is why the motivation again comes from, so these models have been deployed on cloud for the detection of breast cancer. So these models have not been implemented on FPGA. So with this pink Z2, that means it is a very resource constrained edge device. So it has very limited resources like your LUT RAM, VRAM, DSP, all those things. So very limited resource. Can we implement the deep learning model? Yes, but our model should be very lightweight model, as well as it should have less than 2000 or 3000 parameters. So that is the first motivation why we go for the lightweight deep learning model for the diagnosis of breast cancer. So for that, so obviously we had developed one new deep convolutional neural network model for the breast cancer diagnosis using ultrasound images. So obviously our network mainly has 3 convolution layers. So we have put the filter in such a way that, so obviously the total number of parameters must be less than 2000. So how can we make the total parameters less than 2000? So that is, it's very challenging to design the deep neural network in such a way that, so whether it can fit in your FPGA device, as well as we should not sacrifice the accuracy for the detection of breast cancer. So that is why, so based on these two factors, so we have done various experiment to choose the best architecture for our requirement. So that is the first thing is, whatever the ultrasound image is there, so we have resized the ultrasound image into 128 by 128 by 3. So this is nothing but your tensor. So this tensor need to be incorporated to your obviously the deep learning framework. So obviously in the deep learning framework, we have the 3 convolution layers. So in the first convolution layer, so we consider only 4 filters with filter size as 3 by 3 and ReLU activation function. So tell me, what will be the feature map size when we have the first convolution layer? So it is now 126 by 126 by 4. So now when we have this 126 by 126 by 4, so obviously when we go for the batch normalization layer, basically to avoid the overfitting issue, so we normally employ the batch normalization layer. Then after that again, pooling layer. So pooling layer is normally used to reduce the dimension of the tensor. So as you can see here clearly, we have the 2D max pooling layer size is 126 by 126 by 4 after batch normalization layer. If we apply the pooling 3 by 3, so obviously what will be the size? Size is 42 by 42 by 4. Now you can imagine how much reduction we have done already. So previously it is 126 by 126 by 4, but now it is 42 by 42 by 4. Now again, if we will apply the convolution, 2D convolution with same number of filters and same filter size with ReLU activation function, so we got the value as 40 by 40 by 4. Now, so again, we have the batch normalization layer and the 2D max pooling layer. So we'll get the feature map as 13 by 13 by 4. So you can imagine how much we reduce the feature map now. So from 128 by 128 by 3 to 13 by 13 by 4. Now, so again we have considered another convolution layer. So clearly, as you can see, so the new convolution layer has 8 filters. So when we have the 8 filters, so we got the feature map size as 11 by 11 by 8. So similarly, then again batch normalization layer and a 2D max pooling layer. So we got the feature dimension as 3 by 3 by 8. Now it comes very challenging when we have the last max pooling layer. So when we have the last max pooling layer, you can see the feature map size is 3 by 3 by 8. Now, so if you do the flattening, so what will be the dimension of the feature vector? So obviously 8 multiplied by 3 multiplied by 3. So that is equal to 72 dimensional feature vector. So if you will not apply, suppose 3 by 3 pooling, if you apply 2 by 2 pooling, so obviously the flattened layer feature dimension increases. Then again the weight parameter increases in the subsequent dense layer. So that is why we consider like pulling grid as 3 by 3 to overcome that number of parameter issue while designing the deep neural network model. So now as you can see, so after flattening layer, we considered the dense layer with 16 neurons. So once we have the 16 neurons, so you can see 72 dimensional feature vector as the input to the dense layer. Then we have 16 dimensional vector. So tell me how many parameters we have in this layer. So weight matrix with size 16 by 72 obviously, and one bias vector with size as 16. So once we have this 16 dimensional so obviously feature vector, so obviously we have the batch normalization layer and finally the output layer, which has obviously one neuron. So that is the sigmoid activation function. So if it is greater than equal to 0.5, then it is malignant, or if it is less than 0.5, it is benign. So that is why this model is nothing but your lightweight deep neural network model for the detection of breast cancer. Now, so obviously when we develop any kind of model, so the next target is how can we train, validate and test that model. So that is again very challenging in deep learning literature. So once we have the developed model, once we generate the training model, so then only we can generate the RTL post synthesis and implementation part, so that finally we can deploy the model on FPGA. So that is why, so this comes to the training part first. So when we do the training, we require the data set. So obviously, so we consider the two publicly available data set for evaluating the performance, to develop and evaluate the performance of the proposed lightweight deep convolutional neural network. So the first data set is very popular data set, is a Kaggle ultrasound image data set. So it has actually 8116 breast ultrasound images. So out of which 4074 belongs to benign class and 4042 belongs to malignant class. So this data set has both so that means we have the training set as well as one independent set, because when you develop any model, so your training data must not be same as the test data. So that is why separate independent test set is required to evaluate the robustness of the deep learning model. So that is why, so in this data set we have the two sets. One is the training set, another one is the independent test set. So then the next data set, obviously we have considered this as the Mendeley data set. So in that Mendeley data set, we have 647 breast ultrasound images. So out of this 647 breast ultrasound images, so we have actually 437 images belongs to benign class and 210 images belongs to malignant class. Now, so each image size in Mendeley dataset is 500 by 500 by 3. So in this work, what we consider, so we resized the ultrasound image to 128 by 128 by 3. So why resizing is required? So obviously resizing means when we do the resizing, the feature map dimension, spatial dimension reduces. Obviously the number of parameter reduces. As we have the number of parameters is directly proportional to latency, obviously we can reduce the latency. So that is why it is very challenging that what will be the optimal size of the ultrasound image, so such that we will not lose the accuracy as well as our latency is also minimum. So that is why we have chosen 128 by 128 by 3 as the image size. Now, so the next part is, so how can we choose that our architecture is best architecture? We cannot blindly tell that our proposed architecture is the best architecture for the, that means for the detection of breast cancer using breast ultrasound images. So that is why we need to choose various other architectures. So as we can see, so we change the architecture part. Instead of 3 convolution layer with our previous architecture, so we vary the network parameters, like we consider only 2 convolution layer. And so once we consider 2 convolution layers, so that means 1 convolution layer with 4 filter we removed. So that means subsequently we have removed the batch normalization and the 2D max pooling layer. So when we reduce that part, so now we have the new architecture. So we call this architecture as deep CNN architecture 1. So proposed architecture was lightweight deep CNN. So that is why the name was LWDCNN. But this architecture we named this as deep CNN architecture 1. So which has actually 2 convolution layer. Then obviously dense layer remains same. So obviously we have 2 convolution layer. Similarly, we have considered another type of architecture like deep architect CNN architecture 2. So where we vary the filters. So that means it is similar to architecture 1, but here as you can see the number of filters equal to 4 in the second architecture as compared to 8 in the deep CNN architecture 1. So mainly one is like how to reduce the number of convolution layers. Next, to reduce the number of filters in the convolution layer. So that is again the new architecture we have experimented. So similarly, so we also consider the third architecture. So in the third architecture, what we did, so instead of changing the convolution layer, can we change the dense layer neurons? Yes. So because our lightweight deep CNN architecture has 16 neurons, so what we change, so we consider this as 4 number of neurons in the dense layer. So now we have again the third architecture, deep CNN architecture 3. So how many architectures we have? We have the proposed LWDCNN architecture. So deep CNN architecture 1, deep CNN architecture 2, then deep CNN architecture 3. So we experimented with 4 architectures. Now, so which architecture we need to consider for our deployment on FPGA? So that is why the architecture which has the less parameter as well as maximum accuracy. So that is why let us do the grid search, or we can say, so which architecture is best. So let us evaluate the model performance on software, on hardware, such that we can choose the best architecture. But the problem is, so first we need to identify how many parameters are there in each architecture case. Now, so when we do the parameter tuning and other things, so for that the first thing is obviously the model training and evaluation strategy. So how to do the training and validation, all those things. So for that, when we have the dataset is there, so that means that contains the breast ultrasound images. So first thing is we need to divide this into training, validation and test. So what is the purpose of training set? So training set is for the purpose of model development. Now once we get the model, so we need to optimize its parameters. So parameters means, so various hyperparameters are there in the model. So basically when we consider the convolutional neural network, so we have the hyperparameters like number of epochs, then obviously the batch size, what type of gradient descent algorithm you can consider, whether it is a DAM optimizer or we can say stochastic gradient optimizer. So all those things you need to consider. Then also the cost function. So whether you are using binary cross entropy, then you are using the mean square error or focal entropy, all these things you need to be considered. Then once you got the optimal model, then only you go for the final deployment on FPGA. So that is why the first thing is what we consider is model development, that is from the training set. So once we got the model, then you optimize the model using the validation set. So this validation set is for the hyperparameter tuning. So once we have the optimal hyperparameter, so once we have the perfect model with better accuracy, then only we go for the evaluation. So test set is an independent set. So once we have this independent set, we got the optimized model from the validation set, then only we do the evaluation and find out what kind of class we have, whether it is benign class or malignant class. So that is why this is the procedure. How can we do the model training, model validation and model testing for the breast cancer diagnosis using ultrasound images. Now, so when we do the training actually, so for that, so normally when we do the parameter tuning, so we require grid search. So what do you mean by grid search? Now grid search means, so when you have set up hyperparameters, what do you do? So you select various values and evaluate the accuracy. So once we have the best accuracy value, so you can choose that as the optimal parameter. So that is why we have considered the parameter grid like learning rate grid, batch size grid, and epoch grid. So we evaluated the performance of the classifier, or we can say deep convolutional neural network, based on the each parameter set. So once we get the optimal value, so that will be the best parameter. So obviously we consider this as the final model. So we got the value as the cost function as binary cross entropy, Adam optimizer, and learning rate, initial learning rate is 0.003, and also we have the total final epoch is 30 with batch size as 32. Now, so let us see how can we divide training, validation and test from dataset 1. So obviously we consider the 72% as training, 8% as validation, and 20% as test. Similarly, for dataset 1, again we have the independent test set that has already been there in the dataset 1 part. Then again the second dataset. So what we did, because we don't have any independent test set, so we consider the training, validation and test set. So these numbers are mainly the ultrasound images, number of ultrasound images. So as you can see in dataset 2, so we have 314 benign ultrasound images, 150 malignant ultrasound images. In the validation set, 35 benign ultrasound images, 18 malignant ultrasound images. Then in the test set, 88 benign, then 42 malignant images. So once we do the model training, now directly we cannot take the model to FPGA. So once we cannot directly take the model, but what we need to do, so we need to perform various operations when we deploy the model on FPGA. So what are these operations? So one operation is pruning and second operation is quantization. So once we perform these two operations, so basically it reduce the model size. Now, so suppose we have 2000 or 3000 parameters. If you will directly deploy the model on the, because that is in floating point form, so you cannot directly take the model to the FPGA, because the problem is FPGA has limited resource. So what you need to do, so you need to apply the pruning. So pruning can be applied in two ways. So one way is after training pruning. So that means post training pruning. So post training pruning means first you develop the model. So once you got the model, then you apply the training. So in that case, obviously the parameter will reduces, but the problem is the accuracy will be minimized. So to avoid that issue, so what you can do, so you can consider the pruning our training. So during training, you do the pruning. So that means at each iteration, you do the pruning such that, so what do you mean by pruning? Suppose you have 100 by 100 weight matrix. So 100 by 100 weight matrix means we have 10 to the power 4 weight parameters. So let us consider the 50% of weight parameters equal to 0. So once we have the 50% weight parameters equal to 0, so when we do the multiplication and addition, so obviously that part will be deactivated. So you can imagine how much computation we reduce on FPGA. So that is why, so here it comes as the pruning our training. So we apply the pruning our training with sparsity equal to 50%. So sparsity equal to 50% means 50% neurons are deactivated in convolution layer as well as the dense layer, because the weight multiplication normally happens in convolution layer as well as the dense layer. So that is why when we make the 50% of weight values as 0, so obviously we can reduce the computational complexity on FPGA also. So once we reduce the weight values, the next comes to the quantization. So because we reduce, that means we make few weight values in the weight matrix as 0. So the next part is whatever the remaining weight values are there, again that is in floating point 32 form. So we cannot use that for floating point 32 form. So we need to convert it into fixed point representation. So that is why to convert it to fixed point representation, so we can use various like that means different fixed point representation case. We can allocate the bit, like suppose 28. So 28 means 8 bit is allotted for the integer and remaining 12 bit. So that means 20 minus 8, 12 bit is used to represent the fractional part of the floating point number. So similarly, we have the 18.8. 18.8 means 8 bit for integer and 10 bit for the fractional number. Similarly, 12.4. So basically it produces the reduced precision based representation of the weight parameters in convolutional as well as the dense layer. So when I am saying that convolution and dense layer has weight parameter, because the pooling layer is like your dimension reduction, it doesn't have the weight parameter. So that is why convolution layer and dense layer have the weight parameter. So once we got the quantized and pruned model, so now the model is ready to be deployed on FPGA. So before deploying it into FPGA, so what we need to do? So we need to generate the RTL, clear RTL. So obviously, as you can see, so we consider the high level synthesis framework. So obviously, for the generation of RTL for the lightweight deep CNN model. So once we generate the RTL using Verilog, so obviously, so we do the synthesis, implementation as well as the bit file generation from the Vivado itself. Here, and another important factor, like how much, that means how can you use the number of multipliers. So that is why the loop unrolling, resource sharing as well as the data reuse comes to picture when we do the that means implementation on FPGA. So that has been taken care. So when we have the implementation, or we can say the RTL generation. So normally high level synthesis for machine learning tool, so it uses like streams so to implement the convolution layer. So when we have the convolution layer, you have 6 number of loops for the image feature extraction process. Now imagine when you implement this 6 number of loops, obviously it require higher computational time. So to overcome that, HLS for ML normally uses streams to implement the convolution layer feature map. Now, so once we have all those things, so another factor is there. So that is called as the reuse factor. So in reuse factor, so what this reuse factor signifies? So mainly the reuse factor signify that the number of times the multiplier used. So that means so when we consider the same multiplier, so and use the same multiplier 20 times, so what will happen? So obviously we can so that means we can do the parallelization. So that means once we have the reuse factor, we have the increasing value of reuse factor. So in that case, we can reduce the DSP consumption, but at the same time latency also increases. So that is why the selection of reuse factor is again very challenging. So when we need to deploy the model on FPGA, so as we have the reuse factor, once we increase the reuse factor, the problem is DSP we can reduce. So DSP block we can reduce, but at the same time latency increases. So to select the trade-off between these two things, so we consider the reuse factor as 16. So for implementing the lightweight deep CNN model on FPGA. Now, so once we implement the LWCNN model and generated the bit file, then we transfer the bit file to the programmable logic part of your PinkJet2 FPGA. So that means pink jet to FPGA has two things. One is nothing but programmable system. Another one is programmable logic. So in programmable system, so we have ARM Cortex, that is the microcontroller. Now similarly, we have the obviously the programmable logic, so where we can do the hardware acceleration. So we have generated the bit file from the Vivado, so we can take directly that into the programmable. So obviously programmable logic part. So various other image processing operations, so we can perform on your programmable system, like the image resizing. So that means original image is 500 by 500 by 3, you can reduce the image sizes to 128 by 128 by 3. So that can be performed using OpenCV through the ARM Cortex, or you can say programmable system. So that is it. When you implement your deep CNN algorithm, so basically you need to execute the image processing task on programmable system and hardware acceleration task on FPGA. Also, you can do the image processing task on programmable logic. For that, you need to design the architecture. So that is why it is very challenging and open challenge how to develop the architecture for image processing applications as well as for the deep learning applications. Suppose like directly we have applied the deep learning model on image. So can we do the wavelet transform first and again reduce the model? So we can prepare the architecture for wavelet transform. So that is why again it is again challenging how to do the architecture, VLSI architecture, for implementing the wavelet transform, two-dimensional wavelet transform. So that is why it is challenging that how to develop the efficient VLSI architecture for implementing the Haar wavelet, Dobachis wavelet, various wavelet bases are there. So one can select that as the open problem. Now, so let us see the performance of the model. So once we develop, validate and test the model, so we need to measure the performance of the model. So as you can see, so obviously we have tested our model on CPU, so directly the Python framework, and also on pink jet to FPGA. So what we can expect on CPU, obviously we have high performance, and on FPGA, so the performance may reduce. Why reduce? Because we use the reduced precision based representation, pruning, quantization, many things we are doing. So that is why, as you can see, for the first dataset case with hold out validation, so hold out validation means 72% as training, 8% as validation, and 20% as test. Out of this 20% test, so we got the accuracy as 94.15% for database 1. Similarly, the kappa score is 0.883. So when we have the 5-fold cross validation, the accuracy is 91.8289%. So that is the average accuracy. So obviously the kappa score is 0.88837. So when we do the independent dataset evaluation, so accuracy is 86.88% with kappa score as 0.736. And finally, for the dataset 2, whatever the model we got, so we got the performance as 80.76%. So this is for the CPU case. So the performance has been measured through CPU framework. So obviously Python framework run on the inference on CPU based obviously PC. So then we do the inference using pink jet 2. So for the holdout validation, so pink jet 2 obviously on FPGA, the model performance is 93.16% and kappa score is 0.863. You can see that there is a reduction of 0.02 for the kappa value, as well as accuracy has been dropped from 94.15% to 93.16%. So this is the precision level what we have considered at 28. So that means 8-bit for the integer and 12-bit for the fractional number with pruning our training with sparsity as 0.5. Now, as you can see, for the 5-fold cross validation case, 91.89% accuracy for the average accuracy. Now you can see the on FPGA, the average accuracy is 85.36%. Now for the independent data set, the performance is improved. So that means you can see on FPGA, the performance is 88.11, but on CPU, the performance is 86.88. Why? The reason is also when we apply pruning and quantization, it acts like filter. So that means it can delete the, or we can say it can remove the redundant weights. So when the redundant weight has been removed, so in some applications the deep neural network can provide better performance. So that is why, this is the reason why the model performance is 88.11% as compared to the CPU on CPU counterpart, so which has only 86.88%. Similarly, for dataset 2, the model performance remains same, so that means it is 80.76 on both CPU as well as on FPGA. Now, so the next part is obviously, so why we select that particular architecture, lightweight deep CNN architecture, why not other architecture? So when we consider deep CNN architecture 1, obviously we have the accuracy as 94.03. Now you can say how many parameters we have? 22,157. So implementing this parameter based CNN on Pink Jet2 is like, it's very difficult and it's not possible that when you generate the bit file, the Vivado will produce the error because the number of parameter exceeds. So obviously, so that is why architecture 1, although it is giving better accuracy 94.03, but it is not implementable in the Pink Jet2 FPGA. So then comes to architecture 2. Architecture 2, so we have the performance is much better, 95.38%. But how many parameters we have? 11,181. So obviously the parameter is very high. So what model we can select? The third architecture has performance 88.40, but the number of parameters is 913. So it can be easily implemented. We'll get better latency also. That means very low latency. So very low latency as we have less parameter. But the problem is the accuracy is 90, that means 88.40. So when we consider the lightweight deep convolutional neural network model, LWDCNN model, so we have accuracy as 94.15, but the model parameter is 1837. So you can see there is a trade-off between your architecture 3 and architecture 2. So our architecture is associated between architecture 2 and architecture 3. So that means parameter we increase little bit, but accuracy is very similar to that of your architecture. So only 1% reduction in the to the architecture 2, but it is better than architecture 1. So that is why we select the LWDCNN model for the FPGA based implementation. So clearly, as you can see, so we have different fixed point representation, or we can see the precision case with accuracy and also the resource utilization on Pink Jet2 FPGA, and also the on-chip power, that is your static dynamic power generated from the Vivado itself. So as you can see, so we have now the fixed point precision case as 28. The accuracy on FPGA is 93.16%. With LUT utilization is 64%. LUT RAM utilization is 11%. Flip-flop utilization is 44%. DRAM 80%, and DSP 10%. So this can further also reduce if you consider various architectures, like you can use the various other multipliers like Dada multiplier, any other adder also you can explore to further reduce the resource consumption as well as the on-chip power without sacrificing the accuracy. So this HLS high level synthesis normally use the basic architecture. So one can also modify in the architecture level after pruning and quantization to minimize the resources on FPGA. So when we consider 18.8 based fixed point precision case, so you can see the accuracy has been reduced to 64.71. If we further reduce the precision, so obviously the power reduces as well as the resources are less, but the problem is accuracy. So accuracy suddenly reduces. So if you consider suppose 10 and 2 bit for integer and 8 bit for fraction part, so obviously you will get very less power with limited resource utilization, but the problem is you'll have very poor accuracy. So that is why in healthcare engineering, so obviously when we do the FPGA based edge computing, so we need to, the first thing is accuracy as well as the latency. Now, so let us add some interpretability to the model prediction. How the model predicted as suppose benign and malignant. So to so to introduce some interpretability, so we can consider the grad cam and cam, so class activation map. So when we consider the class activation map for the benign case, that means figure A is the ultrasound image for the benign class, and figure C is nothing but your ultrasound image for the malignant class. So for the benign class, as you can see, the ultrasound image, this is the class activation map, and D part is the class activation map for the malignant class. So as you can see, malignant class more activity, and that is why it is more random things are going on malignant class. So that is a tumor is proliferating in case of your malignant part, and benign tumor obviously, so that means it is less dangerous as compared to your malignant, because malignant tumor is like your cancerous tumor. So that means, so obviously we have this as the discriminative feature map that has been learned during your CNN, that means your CNN feature map calculation. Now, as you can see, to further introduce the interpretability of the lightweight deep CNN model, so what we did, so we also consider the TSNE plot. So this is the TSNE plot. So before incorporating to the model, so that means TSNE plot of the ultrasound images. So before using your lightweight deep CNN model, so as you can see, all things are distributed. So that means, so obviously the red thing is like your malignant and the blue things are like your benign. So when we apply the model, so clearly you can see, so we can differentiate between your benign and malignant things. So obviously, so we can conclude that your LWDCNN model produces the discriminative feature map, but further we can improve the accuracy if we increase the number of layers. But again, that is challenging how to deploy that model on resource constrained FPGA based edge device. So we compare with various transfer learning models. So obviously the problem in transfer learning models that though we have very less training parameters, but at the inference phase, so we have many parameters like your million parameters. So BGG16, as you can see, suppose ResNet 50, the 23.59 million parameters. Also, it produces the accuracy as 73.95. As compared to CPU-based implementation of our proposed LWCNN model, so we have the performance accuracy as 94.15%, so which is better than various transfer learning models. So we had also compared with the various existing models on the same dataset. So like database 2, so we consider the BOSNet model, very standardized model, and MSA DIDL model. So based on that, so our model obviously better than MSA DIDL with in terms of parameters, and accuracy has not improved much, but it is 79.88, 80.76. So little bit improvement, as you can see, so almost 1% improvement, but the parameter we have reduced like from 12, that means 1,22,000 to 1837, as well as you can see the simulation time, or we can say the latency. So by considering 1624 images, as you can see for the MSA DIL is 5.21 second, but using the proposed LWDCNN model, it is 0.83. We cannot deploy the BOSNet and MSA DIDL because the problem is these models have huge parameters, more than 1 lakh. So obviously we cannot deploy these models on resource constraint PinkJet to FPGA. So what we did, so we again compare the hardware-based comparison of the proposed model with another lightweight deep CNN model developed by Prabhav Gudati. So obviously this model is different, but it has more parameters, little bit more parameters than our proposed model. So when we consider implementation of that model on FPGA to compare with our proposed model architecture, so obviously we got the higher resource utilization of Prabhav's model, 68% as LUT, 12% LUT RAM, 51% flip-flop, DRAM 83%, and DSP 12%. But our model has less utilization regarding the flip-flops and DRAM with higher accuracy as 93.16. But Prabhav has not applied the pruning. So when the pruning has been applied to his architecture, obviously accuracy will further reduce. So that is why what sparsity based pruning. If we consider 0.1 as sparsity, like 10% neuron actives and rest other neurons, 90% neurons you can deactivate. So in that case, obviously you will get the minimal resource. So that means maybe flip-flop utilization is 10%, but the thing is you have the very less accuracy value. So when you deploy on FPGA, so these things so requires the obviously carefully selection of model as well as the model parameters, then also the pruning, quantization, and all those things when we go for the final deployment, or if we have the better performance on FPGA, so finally we can go for the ASIC based design. So if you have any doubt, you can ask related to this presentation. Yes, Dr. Raj. Any doubt? Any doubt related to the implementation of deep CNN? Yes, so pruning is normally performed on CPU only, not the hardware. So hardware we cannot do pruning. So pruning is CPU only. On we do the dropout and pruning. So normally pruning is considered because dropout is the same thing. So when we do the pruning, so dropout mainly consider like your spatial dropout, and also you can do the temporal dropout. But the pruning is mainly you can have the, suppose like during training, if we consider like 10% of neurons, so what will be the performance? So without sacrificing the validation accuracy, so the pruning is more efficient as compared to the dropout. So dropout is, we cannot optimize the parameters in dropout, but we can here optimize the parameters in pruning based on the validation accuracy. Any other question? Yeah, dimension of weight matrix dimension will not change. Suppose we have 5 by 5 weight matrix. Now if you make the 50% weight values as 0, so obviously the dimension will not change. But when you do the multiplication with feature vector, Suppose you have feature vector as 5-dimensional, your output feature vector is also 5-dimensional. So if you do the multiplication, when the values are 0, so you don't require to multiply those values. So obviously you can reduce the number of multipliers, use of multiplier and adder. So the size of the weight matrix will not change, or the dimension of the weight matrix, but the values inside in the weight matrix, obviously, so this becomes 0. So this will reduce the utilization of your adder and multiplier. But the dimension of weight matrix, that is remains same. Any other doubt? So obviously there is a challenging thing about, you can also modify the multiplier. Whatever the high level synthesis consider, even if further you can modify the architecture and architecture of a multiplier as well as the adder part, such that the deep neural network resource utilization can be minimized. But also for the ultrasound imaging, so if you will get 97-98% accuracy with minimal resource, so that is again very challenging research work. So one can file the patent also if we will get more than 95% accuracy with limited limited resource. So once we have these two things optimized, then only the model will perform very well. So one more thing is, the model may work in one hospital data but may not work on another hospital data. So that is why by synchronizing the model for all hospital data, you can go for the federated learning. So once you got the global model, can we have the FPGA implementation of the global model? So that is again very challenging. So we can call this as distributed embedded artificial intelligence. So that is again very challenging, and lot of things can be done in future. If any other doubt, he or she can write in the chat box.
Hello, sir.
Yes. Sir.
So you have finished?
Yes. I have
Actually, I
finished
was
and also questions
okay.
completed.
So, sir, I have some questions. Actually, I was a little bit busy at that time. And,
Okay. Please ask.
so you have done a lot of good work in that isolating the CNN model to the FPGA.
Yes.
So have you done some architecture development and some what are the stages you are telling about this 2D max polling layer and 2D conventional layer? So all
Yes.
these things you have implemented through the Verilog. You have generated the Verilog.
Yes. So mainly on using Verilog for the implementation of convolution layer, max pooling, then also the fully connected layers. All these layers, activation, mathematical equations, all things have been implemented on Verilog.
So what is the size of this means after quantization? What how many bits you have taken consider means it's a fixed point or a floating point you have.
So we have considered almost six fixed point representations, as in the uh, slide number this one 16. So in
Okay.
16 we have 28 8-bit for integer, 12-bit for the fractional number, then up to 12 4. So five fixed point representation cases we have considered and evaluated the accuracy.
So if you take the fixed point, then accuracy will compromise, I think.
But for the higher, like that means a 28 case, accuracy is much better, 93.16%.
Okay, so that is enough for this any
Because once we get the more than 90% accuracy, so that is good in the healthcare standard for the, that means the
so
model
that is
is
enough. That means for the healthcare 90%.
not enough, but it can be considered. But if it
So
is
if
less
you go
than,
with a higher accuracy, let's say if you go with a higher accuracy, in that case, uh, how much area it can consume? Is it there any means like if I
obviously the
want to go
resource
with a higher
resource
accuracy, so
utilization will be more.
what is the suggestion that you can increase the fixed point size?
So obviously, if you reduce the area, so obviously the accuracy will also reduce. The problem is you can use less bits for the integer as well as for the fractional number. So the problem is when we reduce the area, so then accuracy will reduce, means everything will have the problem like ultrasound image. Obviously the performance of the model in terms of precision, recall, all those things will again reduce. So then it will cause the false diagnosis. So once we have the false diagnosis things, like the person is actually malignant, so that means malignant tumor is there, but it model will predict as the benign. So due to that false diagnosis, there will be the problem actually. So to overcome
So
that,
can we go with this 16-bit integer instead of 8?
16-bit integer, yeah, it can be used, but again, only integer representation, the accuracy will degrade up to 60% or 50%.
Okay.
Because we have already experimented with 8-bit integer, 16-bit integer, as well as floating point 16 using TensorFlow Lite for
So
the
where it is gives high accuracy?
so you for the fixed point representation with 28, so that means 8-bit for integer and 12-bit for the fractional number, accuracy is 93.16. So even if we will go better, like suppose 2210, so 10-bit for the integer and 12-bit for the fractional number, but the resource utilization will be very high. VRAM utilization will be 95%. So and the DSP utilization again increases. The problem is on the on chip power also 2 point something. So
Availability resource and FPGA will also increase it. Means you
yes,
have to go with a higher end FPGA.
but we have but the target is resource constraint FPGA based edge device. So that is why we consider the 28 best fixed point representation.
Hmm. Okay. And sir, if I take it the same AI ML model to for intrusion detection, then
Yes, obviously, but the thing is that the image size must be 128 by 128 by 3. So it can be used for the agriculture related applications like computer vision, agriculture, wherever the image size is 128 by 128 by 3, if we resize the image, then only we can use the transfer learning based things for our proposed lightweight deep CNN model. But for the intrusion detection, so obviously one can do the lightweight 1D CNN. So 1D CNN is again very challenging. If we do the pruning, if we do the quantization on 1D CNN using time series as the input for the classification or regression applications, what will be the model performance as well as what is the resource utilization on FPGA? So that is again very challenging thing. That is, one can explore those things in future also.
Okay. Thank you, sir. Thank you for this clarification. Anyone from the participant, if you want to interact or ask something, you can ask. Okay. I think nobody has some questions. Fine. So, sir, we can thank you, sir, for presenting such a good information and demonstrating. You have demonstrated so many good results also. Hardware isolating the CNN model to the FPGA, which is a very difficult task, I understand. So, thank you for your giving us insightful information. Thank you all the participants. I hope you have learned something from these two sessions, today's session. Tomorrow we have another two sessions, but the first session will start at 11. So we'll share the link by today evening about the session. So please attend the session at 11 tomorrow. Today it was 10 a.m. because of the speaker was from USA, so that is reason we have shifted to 10 a.m. But tomorrow it will again start at 11. Thank you, everyone. Thank you, sir.